this vicinity session. Today's session, we are going to see the vicinity semantic interoperability approach. First, we are going to see what means semantic interoperability. Then, we are going to see the requirements to be semantic interoperable. Following, we are going to check the technical requirements to be interoperable in the vicinity. And finally, we are going to use the semantic interoperability services. Let's start. What is semantic interoperability? Just imagine the next scenario. We have several fridges, each of them from different vendors. Now, these fridges expose data. The problem is that each one of them does that using different access methods. For instance, REST API, local files, or another REST API. Then, another problem is that the different fridges may expose the data using different formats. For instance, JSON, CSV, or again JSON. And also, we have the problem that even if they use the same format, they could have different models. In this case, the different JSON follow different payloads. How we have solved this problem in Vicinity? Well, we have built different layers of interoperability. The first one, here in red, unifies the access method and the format by using REST APIs and JSON. The problem is that the JSON still have different models. To unify as well the model is include a new layer of interoperability. In this case, this layer normalizes the model following the vicinity ontology. The format in this new layer is RDF and the access method is Sparkle. Now, here you can see an overview of the vicinity ontology. It has mainly 5 components. The first one is the ontology of the Web of Things based on the W3C standard, which is used to describe the different types of sensor or services in Vicinity. Then we have the data types ontology that allows to define types of data. Then the core, it's the heart of our ontology and allows to connect the different sub-ontologies that we are seeing here. Then we have the adapters ontology that specifies in very high detail the type of devices we can have. And finally, we have the what mappings, which are used to translate data from JSON to RDF on the fly. Now, going back to our scenario, the semantic interoperability allows to do these kind of things. Imagine we have a gateway, in this case the one of the Samsung fridge, and we want to do the following Sparkle query. What is the fridge's temperature within my neighborhood? So the semantic interoperability will somehow connect with the neighbors of this gateway and ask that information, retrieve the value, and finally answer with the correct values. Here we can see the different temperatures of the fridges in the neighborhood. How this works at low level? Well, first the query is sent to the gateway API, and this forwards the query to the distributed query client. This component is a library of the gateway API and connects with a cloud service called Gateway API Services. This will perform an intelligent discovery through all the different thing descriptions registered in the vicinity. However, the discovery will always maintain the privacy of the contracts, so no data outside the neighborhood will be never discovered. Then the Gateway API Services return a TED, a thing ecosystem description, which will contain only the data relevant to answer the query. Following, after that process and having the TED, if the query required to access data, for instance, in this case to retrieve the values of the temperature, the same distributed query client will perform the access to the endpoints, in this case the fridges that have a friendship with ours, retrieve the JSON and translate it into RDF. Then, altogether, the RDF translated and the description will be computed and an answer for the query will be produced. Let's see now the requirements to be semantic interoperable. First, we need to register a thing description with a service or a device. Then, what we need to do is to have some contracts. In this case, the most useful thing is to have a service and contracts with devices or other services, even though you can use the semantic interoperability services in a gateway that is related to a device. Then, what you need to do is to include mappings in your thing description. This is important because otherwise, a component that translates the JSON into RDF will not be able to do so. And then it's also important to write rich thing descriptions, for instance, with the different locations. And with all these steps, we have met all the requirements to be semantic interoperable. Let's see now the technical requirements. Well, to use the semantic interoperability services, the only thing you need is to have the gateway API and the agent running locally. Then you can just send the queries to the agent. We will see in a few minutes how. We suggest to use the Docker services receipt in the GitHub. You have here the link because it's really easy to deploy them and start querying the cloud of Vicinity. Now, let's see how to use the semantic interoperability services. First, we are going to start the services gateway API and the agent by using the docker compose app command. Then, we are going to open Postman and create a new request. The type of request will be post, and the endpoint will be our agent, in this case localhost 9997. And we have to send the query to this endpoint, agent/sparkle. Then we're going to set up the headers. In this case, we need to specify the content type with application JSON, and then write the adapter ID we specified in the thing description. In our case, it was Hackathon Data Service Adapter, and also the infrastructure ID, which was the name of our access point in the neighborhood manager. Once we have set up this, we can go to the body and write a query. In this case, our Sparkle query is asking about everything that is in our neighborhood. So we can hit the send button and wait the response. And here we can see the response. We have the thing that is observed by this sensor. In this case, inverter consumer active power load, the OID, and the type. In this case is photovoltaic panel. Actually, we only have a contract with a company in the neighborhood manager called Prosumer. We will see how we can know this information in a few minutes. And they only have photovoltaic panels. So now the question is, we can see here that they have different observations. So now the question would be, okay, and can we know to who belong these photovoltaic panels? For such purpose, we created this query, which is actually with this triplet here, asking about the owner. So this query, I'm going to send it, will group by the organization and will count the number of things by type that that organization have. In this case, there is this organization, UPM, which is us, which has one thing. This is the OID, and this is the type. It's a service. So this is the actual service we are querying right now. And then we have this other owner in our neighborhood called Prosumer, the one I was telling you about before, that has 7 objects. And the 7 objects are of the type photovoltaic panel. More type of queries we could do is this one, for instance. So if you remember, one of the requirements to be interoperable was to have rich descriptions. In this case, I'm going to send the query. What we are asking here is to retrieve the location. So we are not specifying to retrieve a city, a building, or a country. We are just asking about any location that in this case, the organization, the Prosumer, included in the thing description. And here we can see the response. So we have 7 objects, which are the 7 panels, and we can see here that they are always located in Bratislava, so they are in the same place. The owner is always the prosumer. We can see here that the location type is always the city. So in this case, this user didn't submit a country or a building space for these objects, very likely for privacy reasons. But here we can see how we can retrieve the location data. And finally, I'm going to show you another query, which is actually accessing the data of vicinity. So in this case, we are asking for different things in our neighborhood. We want to know the type of object, what they are observing, and the value they have. And we wrote here this description, so we only want to retrieve objects that observe a value above 0. An important thing here when we write queries that access data is that the statement that specifies to retrieve the value, which is the highlighted one, has to be always optional, because not all the endpoints have submitted or are submitting the mappings. So if they don't have the mappings and we don't put the optional, we will not be able to retrieve any value. So this statement goes always in this optional. And we hit the button and we can see here the response. So in this case, we are retrieving all this for this PV actual active power, the value for this photovoltaic panel. Something similar with this inverted consumer active power load. We have the 210 value, and so on. This is all about semantic interoperability. Thanks for watching.